Hello, everybody. My name is Basem Aljoumani. I collaborate in this work with my colleague Joseph Sanz. The title of my presentation, Novel Approach to Estimate Soil Solution Salinity, taking data from sensors. So first, I will talk about the problem related to salt-affected soil and how its impact in agriculture and environment. And then I will talk about how we could measure the method to measure the salinity, the limitation of these methods, and our innovation to measure the salinity in the soil. I'm going to use a short video from Food and Agriculture Organization to highlight the problem related to this phenomenon. And we can just about 1 minute, 30 seconds. Thank you today.
Salt-affected soils include both saline and sodic soils. Saline soils contain an excessive amount of soluble salts. The presence of soluble salt makes it difficult for plants to absorb water from the soil. Sodic soils carry high amounts of absorbed sodium ions that damage soil structure. Soils become hard and compact when dry and sticky when wet. Both saline and sodic conditions considerably reduce the agricultural productivity.
Due to soil salinization, 1.5 million hectares every year out of production, and decrease in the production from 46 million hectares each year, and they estimated about annual loss of agricultural productivity about 31 million hectares. If we want to see how this type of sensor, the new devices to measure the salinity there is different type of sensor from different, this is type with examples from different companies who produce this sensor. They install in the soil to take data from the salinity. But the limitation of this sensor, they don't measure the salinity in the liquid phase. When you install the sensor in the soil, so the current electricity goes through the solid phase, liquid phase, solid liquid phase. But we are interested in the liquid phase because this is what the plant sends. For that reason, we need methods to estimate precisely the salinity in the liquid phase. There is model from Herhorsett model that estimate the linear relationship between direct permittivity of the soil and bulk electrical conductivity of the soil. So permittivity is how the soil held the electric charge. And they use this simple equation to estimate the salinity in the liquid. And this type of sensor measures these three variables. So if we determine the intercept of this equation, we can estimate precisely the salinity. But how we can do that, because it is a lot of experiment and each experiment don't have exactly the value that represented the salinity in the soil. Actually, in my research, also in Spain, I installed this sensor in the soil at different depths and get different offset for each depth. And the company said that you have to take one offset for all types of the soil, but I found in each depth there is different intercept when I study this linear relationship. And also I found this linear relationship, it's autocorrelated because the reason for that, because our data is time series. So we install the sensor in the soil, and during the life cycle of the cube, we have time series, and the observation is autocorrelated. So we have to think in the characteristics of our data. And also I get opportunity to talk with the Professor Kalman Campbell. He is the author of a classical book in soil physics, and also he is the co-founder of this company, Digagon, that he produced this type of sensor. And he told me that to estimate the salinity directly, it is very not well worked. So this motivated us to think how we can improve this model. And since our data is time series, so what we did is convert this linear, simple linear regression to dynamic linear regression. That means the coefficient change over time. And in this equation, the coefficient is the salinity. So in that case, we can estimate precisely the salinity. We can see here, this is the coefficient of this linear regression. And when we put the coefficient vary in time, we can see the situation of salinity that changed over time. And when I put here R1, R2, R3, this is the time when the farmer irrigates the field, and we can visualize that when the farmer irrigates the field, the salinity decreases. And also here in Berlin, University of Berlin, I repeat this experiment in laboratory condition. And also I found our finding from this model agree very well with the direct measurement of the salinity. So what we did now, we want to enhance our model by using put another component under to estimate the uncertainty forecasting. For that reason, what we have to do is to provide the probabilistic upper and lower bounds of our prediction. And how we did that? We do that in 5 steps. First, predict from our data from dynamic linear model and the algorithm Kalman filter the salinity, and then to estimate the upper and lower probabilistic. We generate from LSTM model neural network 1,000 time series to get the variability of the offset, the intercept 1,000 value, and from this 1,000 value we get 5th percent and 95th percentile and 95 percentile to build the interval confidence of our prediction. So here we get the prediction of salinity from our data, and from this the scientific data we get the interval confidence of our prediction. So as we see that from using sensor type, we can manage the soil and water sustainability. So we in our research in terms of irrigation management, we save about 30% to 40% from in water compared with the traditional way. And in terms of salinity, we can keep the salinity in good condition for the plant to observe the water. Well, the next step for my work is to use this data, to use this information about the salinity in the grid truth, and to use the image, the salinity image, to do mapping of the salinity for all the area, not just the soil profile that I did this information. Well, thank you so much for your attention.